It's great to be here. My name is Ben Sowell. I'm the co-founder of Aryn, and as noted, I'll be talking about a system we built called Sycamore for dealing with unstructured data. So a little bit about Aryn. We started in late 2022 to bring generative AI to search and analytics. So I think like a lot of people, we started to see the promise of LLMs around that time and started to wonder how we could use it to help larger organizations deal with their unstructured data. We have a great team from great places. We have great funders, and I'm excited to talk to you today. So before I get into the sort of technical details and how we use Ray and what we built, I want to talk a little bit about customers, right? Really, when we started this, we came from an analytics background. We came from sort of structured and semi-structured data. So we really just started talking to people to try to figure out, when they said they had a bunch of unstructured data, what did that mean? And what kinds of things were they trying to do with it? And so here's just a few examples of what we found. So we talked to a number of finance customers, and they have huge amounts of data, SEC filings, earnings reports, board decks, and they were trying to do things like come up with market estimates or come up with customer maps, figure out who were competitors, who were customers, things like this. We had a really cool use case. We worked with an investigative journalist who was actually looking at these really gnarly municipal budget documents, which could be hundreds and hundreds of pages long, and trying to do things like figure out did police budgets go up or down over time? So kind of an interesting use case, but not super easy to do if you just sort of look at it on the face. And lastly, things like marketing analytics, where people have transcripts of interviews with customers and they want to make inferences about the efficacy of their messages. So kind of taking this all together, there's a few sort of things that we kind of took away. One, there's really a complexity wall for AI applications as well as AI infrastructure. So this morning you heard Robert and Jan talk about the complexity wall that you hit when you're building the platform. Things like too many accelerators, models, and so forth. But when we work with these sort of non-tech companies that are trying to build AI applications, they have the same problem, right? The demos look great. They're able to build something on a small little chunk of data over a weekend, and then they try to get into production and they spend the next 6 months just fighting. And there's a few reasons for that. One is that the data is super complicated, right? You get really complicated documents. They can be in PDF, they can be in DocX, they can be PowerPoint, they can be all sorts of other things. And they have a whole bunch of different kinds of modalities, right? Tables, figures, graphs, so forth. Another problem is just that the queries that they want to ask aren't well served by the techniques that are there today. So probably everybody here is familiar with RAG, right? This basic retrieval generation approach. But in reality, that only gets you so far, right? There's some technical limitations, things like context window size or embedding quality. But there's also just the fact that some queries don't fit into that pattern. Things like queries that require sweeping through large amounts of data or combining multiple data sets. One example I like, and this is from a real customer we talked to for a while, they had a bunch of earnings call transcripts. And the question they wanted to answer is, what is the yearly revenue growth and outlook of companies whose CEO recently changed, right? And there was no field that said, CEO changed, right? They just had quarterly reports, and you had to look quarter over quarter to see when the CEO changed. And then based on that, you had to go back and compute some information for those customers. So this is sort of what I would call a self-join, right? As a database person, I think of this as a join. But it's something that requires multiple passes over the data, requires potentially sweeping through large amounts of data. And no RAG system is going to be able to answer this kind of question regardless. And really, all of these things require ETL, document ETL, and data preparation. And that's, we really found to be one of the most important things you can do for these kinds of applications. Right? It's often really critical to extract structured information from these documents, including structured information from tables and figures, in order to augment them, either for straight RAG, because you want to build the context, or for more complex sort of question answering applications that I'll talk about throughout the talk. And we have some data for this. We've measured things ourselves. There was a customer support workload we worked on, and we started out, we were like at 55% with a basic RAG approach. It's just atrocious, right? It's basically random. But with good ETL, we got it up to 97%. And you see similar kinds of improvements on Finance Bench, which is a very challenging open benchmark. So enough preamble. What did we build? Right. So we built Sycamore, which is really a platform built on Ray for tackling the document ETL problem. And one of the cool things that I think we learned here is that it turns out that building a really good ETL system actually helps you with queries as well, right? I'm so used to thinking about ETL as a separate process, as completely separate from your query system. But in fact, there's really a spectrum or continuum between the two. ETL, you can push certain operations, say entity extraction, either to ETL or to query time. And it may have different trade-offs and it may have different characteristics, but it's really a lot of the same kinds of operations. So to help organize the rest of the talk, I'm going to talk about a few key challenges that map to components of the system that we built, and then we'll go through them in order. So the first step in a document ETL pipeline is really understanding the complex documents and segmenting them. So this is the segmentation problem, right? I get a 1,000-page PDF. It's got tables, it's got figures, it's got text. I need to be able to pick out those pieces so that I can then do more complex analytics over them. Once I have the pieces, I actually need to be able to do the ETL. I need to take it, I might need to do some aggregation, I might need to do some entity extraction, some augmentation, and things like this. That's the second piece. And then finally, I need to actually be able to run these queries, right? Which may be these more complex analytic style queries that require multiple passes of the data or multiple kinds of operations. So we built a component for each of these, right? The first, we have the Aryn partitioning service. We built Sycamore for the ETL step. And then we have a piece of Sycamore we call Luna to do queries. And all of these are built on Ray. And throughout the talk, I'll talk a little bit about how we use Ray, some of the things we like about it, and some of the challenges we faced when we use it. Because I think it's important to have that kind of open dialogue. And throughout the talk, I'll use as a running example some NTSB documents. So the National Transportation Safety Board produces a report for every single aircraft accident in the United States. There's something like 190,000 of these collected over decades. And they're just reports. They're PDFs. They're a dozen pages or less. They contain some tables that can have structured information, what was the wind speed at the time of the accident, as well as free text explaining what happened and the cause that they determined. So when I talk about reports and so forth, this is what I'm referring to. So the first piece of a system we built I want to talk about is the Aryn partitioning service. And this is really to solve the segmentation problem. You get one of these reports and you want to identify text, titles, tables, images, and so forth. And you'd think this is not a hard problem, but it is a hard problem. So the standard approach, which we take as well, is to use a vision model to process these documents and chop them up into different components. When I first heard this, and I don't have a background in ML, I'm a data person, I thought this was insane, right? You're taking a document, a PDF, which has sort of strictly more information. You're doing a lossy conversion into an image, and then you're doing a whole bunch of linear algebra to try to reconstruct the information that's already inside the PDF. But it turns out this is the best we know how to do as an industry, and you can actually do a pretty good job. And ours is particularly good. It's 2 to 4 times more accurate. And we've also focused a lot on systems aspects, and so it's also faster and cheaper. It's also a good example of what I would call a compound ML system, right? Because while there is a model that we do a lot of work with, there's actually multiple models and multiple steps in this process. So when you start out, you first have to detect bounding boxes. This is the classic segmentation problem, right? Put a box around each different type of object and tell me what it is. But after you have that, you actually have to figure out what the text is in the bounding boxes, which requires either going back to the PDF and doing some rectangle intersections or calling an OCR model. And then we have a collection of models for specific kinds of data. For tables, you want to pull out rows and columns. For images, you might want to summarize them, and so forth. And finally, you've got to do some post-processing to convert to an output format like JSON or Markdown. I'm not going to talk about every step here, but just to give you a flavor of the kind of work we're doing here. For the first step, we looked around for what's the sort of best segmentation model we could find, and the answer was there wasn't a great one that was both commercially usable, freely available, and worked well across a wide range of documents. So we built one. We took an open architecture, deformable DETR, and then we took an open data set and augmented it with some of our own data called DocLayNet, and we trained that and found it to be quite successful, and it's near state of the art in some of the benchmarks in that domain. And people seem to like it. We've gotten almost 350,000 downloads on Hugging Face, which we were really excited about. So I want to kind of tie this back to Ray. Why? So what, right? Like, why am I here? Why am I talking to you at RayConf? Well, we use Ray in each of the components that we built. And for the partitioning service, we use it in a pretty simple way, right? We use Ray core to distribute all of these different pieces, all of these different components across actors and GPUs. And so it makes it easy, right? We really don't have to think very much about distribution when it comes to these individual tasks. We did try Ray serve for a little while, but again, because we have this sort of compound system, it wasn't really serving the model that was the main challenge we were trying to solve. It was really kind of piecing these things together, and that was ultimately the easiest way to find for us to do it was to use Ray core directly. And lastly, and maybe this is the sort of motherhood and apple pie slide for ML systems, right? It's really important to evaluate and to continue to iteratively improve, right? We see new documents coming into our partitioning service, which you can try today if you want. And they're all new, they're all diverse. There's a huge number of different types of documents. Think about the difference between an SEC report and a PowerPoint presentation, right? They look pretty different. They're pretty distinct, yet we want to be able to handle both of them. So it's important to kind of iteratively improve and measure the model. And it's also, we found to be important to use both quantitative and qualitative metrics. So we use all the standard metrics that people use for segmentation models for document processing, which we look at them every week. We try to improve them every week. But we also can't really beat just sitting and looking at a handful of documents every week ourselves, because you learn a lot by seeing how things fail, not just that they have gotten worse. And the last point here, again, is just that with these compound systems, you have to look at all parts of the pipeline. I think it's tempting to hyper-optimize and focus on just the model weights and try to really get those better. But one of the biggest improvements we've gotten over the past several months is really just changing post-processing, right? Nothing to do with the model, just taking the output of the model and doing something slightly different with it. So keep an eye out for that as well. So the partitioning service, as I said, is really the first step in your unstructured document processing pipeline. The next is to actually do some ETL, to actually take those components and then do something with them. Maybe augment them, maybe embed them, maybe write them out to a vector database. So we built Sycamore to make that easy. So Sycamore provides a Spark-like functional syntax for working with document collection. So if you're familiar with Apache Spark, you'd be right at home in Sycamore. If not, it's pretty straightforward. It's kind of straight line, dotted notation here. So this little, sorry, I keep pointing at my slides, but this little example, you read some data, you partition it with the partitioning service I just mentioned. You extract an entity, in this case authors. You compute some embeddings and write them out. And the goal with Sycamore, and something that we leverage Ray heavily for, is that this kind of script can be run locally for development on a handful of documents and on a cluster with hundreds of thousands of documents without change. And we think that's really important. I think this is a new enough area that people need to be able to play around, and you need kind of scalability at kind of both ends of the spectrum to make it effective. So I want to stop here and make a note about Ray data, because those of you who are familiar with Ray may immediately say, wait a minute, doesn't Ray already have a ETL and data processing system? And the answer is yes. Ray Data is a scalable data processing library for ML workloads. And it has a lot of what we need. It's got a really great sort of execution framework. It lets you do sort of the map and filter. It has some optimizations. But it doesn't quite map to what we needed, largely because it has a different data model. It's still based on Arrow. It still requires some amount of consistency for schema so that it can do things like columnar optimizations. And that's not quite what we're looking for, as I'll talk about in a few slides. The other thing, and this is more of an amusing anecdote, when we first started, and I think this has since changed a little bit, but the Ray documentation said specifically, oh, you should not use Ray datasets for generic ETL pipelines or scalable data science, which we ignored. So we used it anyway. All right, so what's the data model, right? Because this, I think, is sort of critical, right? You want to make it easy for people to express complex pipelines for working with unstructured documents. So we represent documents as trees, right, where the root is the whole document. You might divide it into sections, and then the leaf level are elements which can be typed. So you can have table elements, text elements, or image elements, for example, that correspond to physical parts of the document. And each node has kind of arbitrary key value pairs that can be either sort of system-provided properties, I mean things like paths, or where did the data come from, lineage information, or they can be structured data that you've extracted. Maybe you pass the document to an LLM, you get back some fields, and you attach that as properties. So it's a very flexible data model. These things can be very large. If you imagine a 1,000-page document where each section has a whole bunch of properties. But that kind of maps to what people need when they want to work with these complex documents. And you don't really want to work with just one document is the thing, right? You also need to be able to deal with collections of documents. So the DocSet is our abstraction for a collection of documents. This is the equivalent of a data set in Spark or in Ray. You can work with a collection of any size using a single data structure. So when I say docset.filter in this particular example, it runs over all of the documents in the DocSet. It can be used to process that way. And DocSet operations can also span multiple documents to make it easier. So sort is a simple example, but you could imagine clustering, you can imagine group by aggregation. These sorts of things are very hard if you wanted to implement them in some of the other kind of single-threaded, sort of straightforward libraries you might encounter to work with unstructured documents. A lot of the simple things don't let you perform these cross-document operations that we thought were pretty important. And what do the operations look like? Well, there's a kind of a combination, right? So there's a bunch of traditional ones that you'd be familiar with if you've looked at data processing systems, map, filter, sort, aggregations, and so forth. These we largely leverage from Ray Data, right? We kind of take advantage of all of the work that the Ray team has done. But we also have a number of semantic transforms, things that leverage ML or other kinds of techniques to try to do the best we can to pull out information or come up with additional metadata about these documents. So I would call partition that, though it's maybe not exactly the same because it's, again, using our partitioning model, computing embeddings, and also sort of a generic LLM query operation, which lets you send sort of arbitrary subsets of the document to an LLM to be able to extract specific information. So rather than just define all of these for you, let me walk through a brief example and give you a flavor of how you might write a Sycamore script. So I'm going to go back to the NTSB documents for this. So suppose you have the NTSB documents, you want to do some initial processing, you want to partition them, you want to extract some metadata, and you want to write them out to a vector database. So this first snippet of code reads the data, partitions it with the partitioning service, and then performs a transform, summarize images. And summarize images is a transform we wrote. It's part of the library. It passes all of the image elements in each document to an LLM and asks it to convert those to text that it then returns and attaches as a property. So you think about it, if you want to use a text embedding model, you need a text representation for the images. This is a way of converting all of your images to text. You could, of course, write a custom prompt to do it differently if you wanted. You could, of course, also use a multimodal embedding model to be able to embed images directly. There's lots of different alternatives, but this is one that is easy to do with Sycamore. The next step is to extract some metadata. Right, so suppose here we want to get the location, date and time, and aircraft of each incident, of each document in the collection. Well, I can just declare the schema of what I want here in this kind of JSON-like way. We can also use Pydantic, and then pass it into an extract properties call. And we will do, again, pass each document through an LLM, deal with all of the retries and throttling and stuff, get the results back, and attach it as metadata to each document. Again, lots of ability to customize, lots of ability to do custom prompts. This is a zero-shot approach where we just try to extract given a single schema. You could, of course, provide examples and get better accuracy. There's lots of approaches, but we try to make it as simple as possible to do the common kinds of operations. And finally, we embed the data with a local embedding model and write it out to a vector database, in this case, OpenSearch. So relatively small amount of code to perform a lot of different operations. And the really nice thing about this is it works the same way on a single document. Right? We routinely demo this on around 100 documents, kind of live. Or you can run it on 100,000 documents. And we've done that as well overnight on a multi-GPU instance. and it runs to completion just fine. And that's really largely because of the Ray backend. The last thing I'll mention, or not the last thing, another thing I'll mention for Sycamore is the importance of materialization. So one of the things in this AI and unstructured world is that individual operations are very expensive, both in terms of time and money, right? Like these ML models take a long time and can be expensive to run. I remember when I first joined, someone gave me 10,000 PDFs and said, please process these. And I thought, oh, no problem, 10,000 is a tiny number coming from the sort of semi-structured or structured world. And then it ran for 10 hours or something at the time because I was doing some heavyweight embeddings or something. So because these things can be expensive, because they can be non-deterministic, it's important to have a way to save your work and to be able to incrementally checkpoint. And so we added a transform called materialize, which lets you save state to stable storage, S3, or local files, which you can put in between any transform, or you can automatically configure to run between any transform so that you can share data across jobs or avoid multiple executions. Ray already has ways of materializing things in memory. This just makes it easy to materialize things to disk because we've all been there where we set something to run overnight and then it fails halfway through and you have to restart it. I can talk a little bit about the implementation on Ray. So Ray is built on Ray data. We start with a DocSet. We build a plan using the operators I mentioned, the Sycamore operators, and then we basically convert that into a Ray plan of dataset operators that then get farmed out to actors and tasks. So we're really leveraging Ray data for the basic distributed operations, map, aggregate, sort, things like this. And then we can get kind of for free the optimizations that Ray has built in, like operator fusion. It also gives us tight integration with the Python ML ecosystem, which is one of the reasons we picked it initially. Right? Python is clearly one in the ML space, and it's nice, having spent many years in Spark and dealing with the integration between the JVM and Python, it's nice to work in a system that is Python native. There are some challenges working with Ray, which I thought would be interesting to put up here and just get people's thoughts on. One that we see that's probably different from what a lot of the other talks are covering about Ray is the challenge of scaling down. So as I mentioned in this world, a lot of people want to start with small data. When they want to start in a Jupyter notebook with 2 or 3 documents and just get a sense of how things work. And Ray can do that, and it's not great that it can do that, but there is quite a bit of overhead on those smaller, faster operations, and it does feel slower. And so I think we've actually been experimenting with a non-Ray kind of local mode, where we have a slower, single-threaded implementation of some of our transforms that you can run just for the purposes of getting started. And I think it'd be interesting to think about how to incorporate that into Ray or how else you might want to solve that. Debuggability is also a constant challenge. It's not really Ray's fault. Every distributed system has this challenge, but I think Ray has an opportunity to do something more. But I think it remains a challenge, right? Even just getting logs back consistently is sometimes hard. And lastly, I alluded a little bit, the data model, we're kind of abusing in some ways, right? We're effectively converting our tree-based documents into just blobs that we pass around in Ray. We aren't able to leverage some of the vectorized processing, some of the more complex, or more, I should say more sophisticated handling of different data types, largely because there are some limitations. Things like, schemas have to be the same across all the documents, where in fact, in document processing, that's not usually the case, because if you imagine, for example, the city budget data set, 2 different cities don't format their documents in the same way. And so the properties that you're able to extract may be slightly different. I'm running a bit short on time, so I'm going to go through the last part of this quickly. And this is not intended to cover this in detail. This is really kind of a teaser for what could be a separate talk. But as we talked about earlier, a lot of queries go beyond RAG, and they're really analytics queries. They involve analytics operators, scans, aggregations, joins, et cetera. And these are really the same operators that I was just talking about for ETL. So can we use the same system, Sycamore, to build a query system in addition to using it for ETL? And the answer is yes. So we have Sycamore query, which takes an English language question, uses an LLM to convert it into a logical plan of operations. So, as a database person, very natural, convert it to a tree of query operators. We then take that, convert that to a Sycamore script, and execute it. So I have a lovely demo I can show you sometime separately. I don't have time in the talk, but you can ask questions over the NTSB data, things like what was the breakdown of aircraft type for incidents with substantial damage, and it'll give you accurate responses and show you how it got to those answers. So I know that was quick, but just a few concluding thoughts. This document processing area is becoming increasingly important for a lot of applications out there. RAG kind of, I think, got everybody really excited as, hey, this is a way I can use my enterprise data with LLMs, but it's not enough. And we have to kind of go beyond that initial step to build real practical systems. The Aryn partitioning service and Sycamore is our take on it. And we think it gives you an end-to-end experience for processing documents and building complex AI applications. And Ray is a great platform to build on for that. And the last piece, again, ETL and analytics can leverage the same infrastructure. I think it's a cool observation. I think it's something that we're getting a lot of mileage out of, and I think it's worth sort of folding back in some of the ETL work into the kind of more traditional query processing. Thank you very much. There's lots of ways to find our work, and I'd love to take questions for a couple of minutes. Yeah, if you wouldn't mind coming up to the mic, that would be great. Yeah, please.
So thanks for the talk. I have a question on the ETL part of the things.
Yeah.
I wonder, if you mentioned, you structure the document in a tree shape,
Yep.
structure and whatnot. Is it possible to represent that and store that somewhere? And then, you can repeatedly run different types of queries or analytical, analysis on top of, huge amount of data. What's your thoughts on that?
Yeah, so, I guess there's a couple of answers. So I talked a little bit about materialize, which is a way of saving those for this sort of repeated, I need to run multiple ETL jobs or multiple queries over that data. I think there might be a separate question, which is how do I index this data so that I can actually efficiently access pieces of it? And that's something we're working on. We have, I showed you a little bit in the script. We can take this, basically flatten the tree and stuff it in a vector database or really any kind of database that will accept records of that type. We're also working on a more sophisticated reconstruction so that I can put the document, this tree structure, in the database and then get it back out and kind of have that one-to-one mapping and keep track of all the IDs. So it's a good question. Part of it's there today, part of it's in progress, but good idea.
May I know if you have a use case for the handwritten extraction for the task?
Yes, we've seen it a lot. Our current model does not solve that, so if you try it today, it probably won't give you great results, but it's something we've seen and we are working on. Forms are a big use case where people have handwritten forms. Yeah.
Go back to the last slide with your links.
Sure. Question was just to go back to the last slide with the links. Of course. Any other questions?
Thank you for the talk. Can you expand a little bit about materialization part and checkpointing? This is probably interesting.
Sure, yeah. So basically, the DocSet, in the same way that Ray Datasets, basically build up a DAG of computation, right? Every transform is another node in that DAG. So you build up the DAG and then you execute it. And so materialize basically says that at any point in that DAG, you can write out the results, which is a DocSet itself, to storage. It's stored in a pickled binary format that's easy to recover. And then the next time you run the job, you can either tell it to recompute from scratch, or you can tell it to just go ahead and read from what you've already materialized. And so this is super useful for development, right? How many times you run some complex first step, say partitioning, and then you're trying to iterate on some code to do the next step of processing, and you don't want to repartition. So it kind of solves that very easily. You can also share materialized data sets with other people so that they can run it. Yeah, it's very useful for development. I think we've all been happy with it. It's not a new idea, right? Lots of people are able to checkpoint things, but I think that what makes it a little bit different in this document world is, as I said, just the expense of each of the individual steps, that it's just extra important to not only persist it in memory, but to persist it on disk, and so that you can recover it in the case of a failure or that you want to rerun something. Got 45 seconds left. Anybody last questions?
Have you evaluated replacing like your image segmentation model and like any OCR to extract text from documents with like a vision LLM like Copali?
Yes, good. I was hoping somebody would ask this question. It's a great idea. I am excited to be able to do that. I think there are a couple of answers. So one is, we haven't quite found the current VLMs to be able to get data out of tables specifically. That's a place that it just has not quite there. I believe it'll get there someday, but I think that's a place where we need something separately. The other thing with the Copali approach itself, and Copali, for those who don't know, basically says for these kinds of RAG applications, don't worry about getting any kind of data out of your PDFs. Just take images of each page, embed the images using a fancy embedding model, and then use a VLM at query time to basically pull out the data that you need. It's kind of a trade-off between what you do ahead of time and what you do at query time. And so for some of the queries that need to do scans or need to process a large amount of data, running the vision model on all of that data at query time is probably prohibitive. And so there's some advantage to doing it in ingestion time. But there may be places where we want to do that as well. So the answer is today it hasn't quite been good enough for us to move there, but we're keeping an eye on that space very actively, and it's something I'd love to be able to do more with. Cool. All right. Well, thank you very much, everybody, and I'll